So, you've decided to pursue biology in some form or another and started taking the first and arguably the most important biology course of them all, Bio 181. At least this is what it's called at ASU, but these videos will work for any equivalent class at any other university. This course is jam-packed with fundamental knowledge that you will need to know if you plan to progress to more advanced biology courses in the future. And even if that isn't your plan, you still need to pass this class. This is where I come in handy. I've taken these classes and realized firsthand the information you learn in this course is absolutely crucial when moving forward with biology and chemistry alike. Where are my manners? I didn't even introduce myself. My name is James Alanya, and I am making these videos along with my trusted colleague, Sophia Zimmerman. We both attended Barrett the Honors College at Arizona State University and created these videos for our honors thesis project. By the time you're watching this video, we will have our bachelor's degrees in biomedical sciences and biological sciences, respectively. So we've been through the struggle that we're trying to help you with. This class can seem quite daunting at times, but don't worry. We will utilize all of the knowledge we've gained over the years to make sure your experience is even better than ours was. So, without further ado, let's get into this series and learn some biology. One of the very first things you will always learn in intro biology courses is the scientific method. Now, I understand that the majority of people watching this video probably already know what this is and are groaning. And I get that this was drilled into your head multiple times in high school and even grade school. But this is an important concept to understand, I promise, so just hear me out. The scientific method is a way of thinking and developing hypotheses so scientists can effectively and efficiently research concepts. It involves first observing whatever one is trying to research. While observing, you may start to wonder and ask questions about what it is you're observing. You would then create a hypothesis for why you observe this occurrence and experiment to test your hypothesis. Once you would finish your experiment, you would collect all of your data and draw any conclusions you may have come to. Let's use an example. Say that there is an ice cube on a table and I observe that over time, the ice cube melts and turns into water. I would then question why this ice cube melted instead of staying in its original state. I notice that it's particularly hot near this table, and ice cubes are typically created in colder climates, so I hypothesize that ice cubes melt because of high temperatures. Once I've created this hypothesis, I create an experiment. I take 3 ice cubes and set them in 3 identical spaces, with the only difference being the temperature in which they reside. It's important to note that I said identical spaces. In order to draw sound conclusions, you need to make sure that you're accounting for any inconsistencies, such as the surface the ice is lying on, the amount of light that may be shining on the ice, and even where the water is coming from to create the ice. All of these should be identical for all 3 spaces, with the only differentiating factor being the temperature. Back to the experiment, I will set the temperature of the first space to 32 degrees Fahrenheit or 0 degrees Celsius. Get used to Celsius measurements, as these are used way more often than Fahrenheit in both biology and chemistry. I will set the temperature of the second space to 10 degrees Celsius and the temperature of the third space to 20 degrees Celsius. I will wait 10 minutes and return to obtain my results. When I get back, I notice that the ice cube in the first space hasn't melted at all, while the second space has some water surrounding the ice cube, and the third space is entirely water and the ice cube is nowhere to be seen. Since I ruled out all other factors, I can come to the conclusion that changing the temperature can affect how an ice cube melts. I can then state that my hypothesis is supported by the experiment that I conducted. Simple enough, right? The scientific method in itself is not a difficult concept to understand. However, it can be used in quite complex situations considering that most scientists follow the scientific method today. I say most because there are other more recent methods that certain scientists follow, but that's not the point of this video and is unnecessary to know at this time, so forget I said anything. Moving on, I want to break down the previous experiment even further and discuss some important terms, specifically independent variables, dependent variables, and controls. Independent variables in an experiment are the variables that you're manipulating to test a hypothesis. If we were to look at the ice cube experiment from earlier, the independent variable being demonstrated would be the temperature differences between the 3 spaces. Dependent variables, on the other hand, are going to be how the object/organism/environment reacts to the independent variable. If we look back to the ice cube experiment, the dependent variable would be how much the ice cubes melted in each space. Think of it as the effect that you're looking for in the experiment. A good way to remember these is that the dependent variable depends on the independent variable. And the independent variable doesn't really depend on anything because it's, well, independent. So if you ever find yourself struggling to understand which aspects of an experiment are independent compared to dependent, you should ask yourself, what depends on what? If we use this question to figure out the ice cube experiment, for example, we would come to the conclusion that the amount of melting the ice undergoes depends on the temperature. Therefore, the amount of melting would be the dependent variable, and the temperature would be the independent. Lastly, we have controls. Controls are included in an experiment to make sure that you are only experimenting on one specific aspect while ruling out all other aspects. Remember when I was talking about making sure to have 3 identical spaces for the ice cubes in that experiment? I was implementing controls to make sure we are only studying the difference in temperature. Think about it. If I just had 3 ice cubes and was trying to test how temperature affects how they melt, and set them on 3 different surfaces with 3 different amounts of light hitting them and got the water from 3 different places, I would still obtain results. But I couldn't definitively say that the temperature was the only reason why they were melting at different rates. All of these other aspects could be affecting the melting rate, which would mean my results aren't very reliable. Controls are extremely important in every scientific experiment to make sure we are testing for one variable. That should be about all you have to know on this topic, so let's recap. The scientific method is a very fundamental concept that you should understand when performing experiments. In order to follow the scientific method, you would begin by observing a phenomenon, ask questions about said phenomenon, create a hypothesis as to why that happens, perform an experiment to test your hypothesis, collect your data from the experiment, and finally come up with a conclusion based on your evidence. You would have to make sure that you have a reliable experiment by involving independent variables, which are variables that you as the researcher would manipulate, dependent variables, which will change depending on how the independent variable differs, and controls, which are consistencies throughout an experiment that will never change, so you can focus on the variable that you are testing. Thanks for watching. Our next video is going to discuss introductory chemistry, where we will talk about atoms, molecules, and water. So feel free to check it out if you want help with that.